Over the years, hundreds of different types of elements have been developed with various stiffness matrices, various degrees of freedom, and various capabilities. In general, though, there are these basic structural types where we have 1D, 2D, or 3D linear elements and beam elements. These are called 1D elements, even though they can be used to represent a three-dimensional structure, such as a beam or a link. The reason they're called 1D is because they show up as lines in most pre-processing. But each of these nodes can have degrees of freedom in 3 dimensions. Then we have 2D elements, and these are triangular elements or rectangular elements, and they're called quads or hex elements. And these elements have either 3 nodes or 4 nodes. They're 2D because they represent, usually they represent thin shells and plates. These are commonly used and very popular elements when modeling thin-walled structures. Then we have full 3-dimensional elements, and they take on these various shapes. A tetrahedral element, often called a tet, looks like this. A hexahedral element, brick or simply a hex, looks like this element. And then we have 3D prisms and 3D pyramid elements. These down here are not nearly as popular and commonly used as these here. In most 3-dimensional solid modeling, you will use these types of elements. So I want you to be familiar with this classification of 1D, 2D, and 3D, and also what a rectangular quad hex would represent. If I said draw a 2-dimensional hex element, I'd expect you to be able to draw this. Or if I said draw a 3D hex element, I'd expect you to be able to draw this element. We're now going to look at each of these element classifications in a little more detail. So 1D elements, they are classified as 1D because they appear as lines. They certainly can have and model 3D structures. Links and beams are both considered to be 1D elements. And the big difference between links and beams are the degrees of freedom. A beam element will allow rotation, where a link element does not allow rotation and just has translation. So links, rods, or truss elements are all represented by the same thing, and these elements are used when there is only axial tension or compression, and they only have axial degrees of freedom at 2 nodes on the ends of the element. The moment of inertia is not needed in these elements because the only stress that can be computed is sigma equals F over A. There can't be any MC over I. And these elements are used in trusses, bridges, and large steel structures. They are computationally very efficient, and when using these elements, the accuracy doesn't improve by dividing a single member into multiple elements, and that's because P over A is constant throughout the element and doesn't change, like where in bending the moment is changing. The element represents a pinned, jointed structure, and bending is not considered. The element is used to model trusses, sagging cables, links, and springs, among others. You'll probably not use this type of element much in the design and analysis of machine components, and that's because it doesn't handle bending. It would be used more in the design of large structures such as steel frame buildings, bridges, and scaffolds, where the number of degrees of freedom can become quite large, and you would want to use this element to limit that number of degrees of freedom. So again, in machine components, I would encourage you to use beam elements in most cases and not use rods or links. But if you're modeling really large structures or where there's a high number of elements and degrees of freedom, you can use these to keep the number of degrees of freedom down to a workable size. Beam elements are grade elements. They're very commonly used. Again, they show up as lines, so they're called a line element. Again, like the link elements, they have a node at each end, and they have both displacement and rotation degrees of freedom. And these elements are widely used in structural components where bending occurs. Shear center and warping can be modeled using these elements as well. And a full 3D beam element has 6 degrees of freedom at each node. So at each node here I would have translation in the X, Y, and Z, and rotation about the X, Y, and Z to have 6 degrees, a total of 6 degrees of freedom. Beam elements are computationally very efficient and are commonly used in modeling building structures and frames, bridges, scaffolds, and aircraft. There are several versions of beam elements that allow various conditions. Beam elements can support nonlinear analysis, plasticity, large deformation, and nonlinear collapse. And multiple materials can be used in layered structures such as composites and reinforced sections. You need to be careful when selecting a beam element so that it gives you what you need but doesn't model something that you're not trying to model. A 3D beam element is shown down below. But here again, in vibration analysis, you need to make sure that certain properties of the beam are turned on, such as shear deformation and rotary inertia. Whereas in a typical static model, you would not need to have those quantities. So beam elements are very popular. They look like link elements. The big difference between beams and links is the degrees of freedom, where the beam element can have rotations and the links, rods, or truss elements, all of these are the same type of element. They just have the same different names for the same thing. All of these just have translational degrees of freedom. So moving on to look at shell elements. These are 2D elements, and they're very popular elements. They do a great job of modeling two-dimensional structures. These elements are used when members are thin in one dimension. In general, when the maximum unsupported dimension of the structure is at least 10 times the thickness, shell elements can be effectively used. If a sheet of paper can be formed into the structure, shell elements can probably be used. These elements are like beams in that they have displacement and rotation degrees of freedom at each node. The default is to have the nodes at the midplane of the element. However, some commercial codes will allow the nodes to be shifted to the surface. These elements are used for aircraft skins, sheet metal formed parts like car hoods and doors, walls, and plates. And they are used to model membranes, plane stress, plane strain, and axisymmetric solids that occur in pressure vessels, plates, walls, and panels. They are also used to model composites, where each individual lamina can be defined. You need to be a little bit careful when using shell elements because they double up. So if I have a thin-walled structure here shown by these elements and another thin-walled structure that combine, I actually get an overlap in the strength of the material. So if this joint is critical, then I am improperly modeling it using shell elements, and I'd want to use a solid element model where I didn't get that overlap. The same thing if you're combining two plates that occur at 90-degree angles. You're going to actually have a gap up here in this corner, and you'll have a doubling of the material down here in this corner. So connecting shells with solids can also be tricky because they don't share the same degrees of freedom. So if I have shell elements in one part of my model and I want to connect them to a solid model, I need to be careful and set constraint equations. In order to couple finite elements that have the same degrees of freedom, or to couple finite elements, they have to have the same degrees of freedom. So this is nice because we can couple shells and beams because they both have translation and rotations. But we're going to see here in a minute that solid elements do not have rotations. They only allow translations. And so to couple shell elements to solid elements can be tricky, and we need to set constraint equations that reduce and limit the rotation in the at the nodes that couple to the solid elements. So in summary of shell elements, they're great for thin structures. They're used a lot. They're computationally efficient, but you need to be careful when you join them, such as this joint shown here and the joint shown here. So our next type of element are solid elements, and these elements only have degrees of freedom at each node that are displacement degrees of freedom. They do not allow rotations. So if you had a sheet of paper 2D or a long metal ruler 1D, that structure could be twisted. However, if you have a solid like a brick or a rock, it can't really be subjected to very high bending or torsion, and so solid elements have been developed with displacement degrees of freedom only. There are several geometries of solid elements, and each geometry has its most effective use. So solid elements continued. There's two basic types, tetrahedral, and tets are usually the default solid element type because they can form about any shape. And they are called simplex, which means they can mesh any 3D volume regardless of shape or topology. And they work well with mesh refinement algorithms. Hexes or bricks, these elements were some of the first elements developed. Brick elements can greatly reduce the number of elements needed because they can have very high aspect ratios, so length of long side to short side, where with tets most algorithms try to keep the lengths of the sides close to equal. It's good to use bricks when you know the solution varies gradually in a certain direction and you're not really interested in the stresses in those regions. Hex elements have been historically more accurate, but the differences are minor. So if you can use hex elements, brick elements, you're usually going to have a little bit more accurate of an answer than using tetrahedral elements. But the nice thing about tets is they can mesh about any topology in any structural shape that you have. So again, in summary, we have back here links, rods, or truss elements that are all the same element. They can have displacements in 3 dimensions at each node, and each element has 2 nodes. Then we looked at beam elements, and beam elements have displacement degrees of freedom at each node, as well as rotations at each node. Then we looked at shell elements, and shell elements are 2D elements. They are like beams in that they have rotations and displacements at each node. Then we talked about solid elements, and solid elements are 3D elements, and they only have displacement degrees of freedom at each node. So that we now want to talk for a minute about what we call element order. An element order refers to the polynomial order of the element's shape functions. And the shape functions are the mathematical functions that give the shape of the results within the element. So we have the nodal values, and then the shape functions take those nodal values and represent that quantity throughout the element. So FEA solves for the degree of freedom values at the nodes. And then shape functions allow us to map these nodal values throughout the remainder of the element. And element order then refers to the order of the polynomial that is represented by that element and the shape function in that element. Shape functions represent an assumed behavior for a given element. How well the shape function matches the true behavior directly affects the accuracy of the solution. So when you choose an element, you are essentially choosing the degrees of freedom and the shape functions. Linear elements typically only have corner nodes, where nonlinear elements have a mid-side node. For shells, the difference between linear and quadratic is not as significant as it is for solids. For solids, higher order elements can greatly improve the results, especially for the stresses. Besides linear and quadratic elements, p-type elements, which have a form of a quadratic to 8th order polynomials for displacements, can be used. So in linear elements, they support a variation of displacement, but since stress is computed from the derivative of displacement, only a constant state of stress within the element is modeled. And this can force a large number of elements if stress is the desired quantity. These elements are highly sensitive to element distortion and typically only provide acceptable results if the goal is to obtain nominal values for the stresses. Quadratic elements, they support quadratic variation of the displacement and a linear variation of the stress within the element. These elements can represent fillets, rounds, and other curved surfaces and edges more accurately. These elements should be used if accurate calculation of the stress field is needed. These elements typically give better results than linear elements and can do so in some situations with fewer overall degrees of freedom. So that's a little bit about shape functions. Again, the element order is based on the order of the polynomial used in the shape function. And the shape functions are the mathematical functions that give the shape of the results within each element. Here's an image showing the difference between tetrahedral elements and brick element mesh. Here in this mesh, they have used 145,000 elements with 730,000 degrees of freedom. And you can see that the mesh is very dense. And here I can use solid elements that are brick elements, and I can get away with about half the elements and 414,000 degrees of freedom using a mapped mesh. So in terms of a solid element summary, TETs typically require less user interaction and support adaptive meshing refinement. If the solution varies slowly, use bricks or prisms because the high aspect ratios can be used, and always perform a mesh refinement using this type. I want to now talk about some important steps in setting up your finite element model. The first one here, so even if you just need a quick number, the main goal of a finite element analysis is to understand the system. Always design simulations so that you can at least qualitatively understand the results. So make sure that when you do a finite element model, you can set it up so that the stresses or the deflections or whatever you're computing can at least qualitatively make sense, and then get the actual numbers from the finite element model. Define the goal of the simulation as precisely as possible. Which question is to be answered? What quantities are to be calculated? One of the most common errors in setting up a simulation is to not have a clearly defined goal. So make sure that if you're setting up your model and you're wanting to know the displacements, that you have identified that as your goal, or if you want to know the stresses, because those goals or those details are critical to setting up the model correctly. Formulate the expectations for the simulation result beforehand and make an educated guess of what the results should be. If possible, estimate at least some quantities of the simulation using simplified assumptions, and this will make it easier to spot problems in the simulation. Number 4, what is the required precision? Do you need an estimate or a precise answer? Number 5, if the model is complex, create it in several smaller steps with verification of the smaller steps. If there are errors, they are much easier to find in smaller models than in one big model. So set your problem up, and if you're able to break it into smaller parts and solve those smaller parts and then add on to it and solve those parts and grow your model, you can make sure that your model is correct a lot easier than just looking at the big entire model at the very end. Be careful with definitions of elements, materials, loads, boundary conditions, and units. Make sure that they are all what you want them to be. So in planning the analysis, there are several things that need to be considered. We need to consider the analysis type, the material models that we're going to use, the geometry, details, and any simplifications to that geometry. We need to pick an element type, and any potential options of that element type should be considered. And then we need to think about boundary conditions, constraints, supports, and loads. So we will now talk about each one of these decisions so that you have a little bit more to go on than what you've been experiencing so far. So in types of analysis, we consider two questions. Mainly, do we look at a static or a dynamic analysis? And then do we look at a linear or nonlinear analysis? So a static analysis assumes that the inertial and damping effects are negligible. Time dependency of loads is a way to choose between static and dynamic. If the loading is constant over a relatively long period of time, choose a static model. In general, a rule of thumb, if the excitation frequency is less than a third of the structure's lowest natural frequency, a static analysis is acceptable. For most everything we do in this class, we will use a static analysis. But dynamic analysis can be very exciting and fun stuff to do, where you look at a transient response or a steady state response due to harmonic and time varying loads. So dynamic analysis is very powerful, and you can do lots of really cool stuff with it. Then we have nonlinear or linear, and there are several types of nonlinearities that can occur in FEA, and these include geometric, material, and contact elements. So geometric nonlinearities, these include large displacements and rotations. So if your displacements aren't small, like we need to assume in many of our hand calculations, then we need to turn on large displacements and look at a nonlinear analysis. But most commercial software packages are more than capable of doing that. These can also include modeling of cables, membranes, and spinning structures. 5% strain is large, and a nonlinear geometry would likely be used. So this would be like 0.05 strain, where if you remember the strain for Young's, or for the yield strength, is 0.2% strain, so 0.002. So large strain is this value of about 0.05. Material, these include plasticity models, hyperelasticity, creep, viscoelasticity, and viscoplasticity. So it depends on if you have these things occurring in your system, then you should account for them in the material model. Contact elements are nonlinear. So this is when two different bodies are in contact. And they can account for bonded and nonlinear contact where the parts can separate. They can also allow for sliding. So there are contact sliding friction coefficients and stiffness coefficients that need to be added in contact elements. So there's lots of ways a finite element model can be nonlinear, but mainly it is nonlinear in the geometry, nonlinear in the material, or nonlinear by the use of contact elements. So those are the analysis types and some discussion of that. Now let's look at material models. The material properties in finite element analysis have a huge impact on the results, and it's important to recognize that the material properties in models used are only approximate. So here's some material models and issues to consider in your material model. Is the material linear or nonlinear? And that has to deal with the modulus of elasticity and the region at which you're using that material. Is the modulus of elasticity, and is that a linear relationship, or is it nonlinear over the loading conditions at which you're looking at the material? Is the material homogeneous? Is the material iso, ortho, or anisotropic? Is there a temperature dependence that needs to be considered? Is there a rate and time dependence with the material? Will the stresses stay in the elastic region? Should creep or fatigue be considered? And so there's lots of these issues that need to be considered when picking your material models. And most commercial finite element software packages will allow you to change the material models and account for many of these effects. Down here is a chart that was developed by Andrew Crocombe for material property, or for material nonlinearity. And I really like this chart. It's a little too complex to go over here, but I encourage you to spend some time looking at it. To begin with, it looks like it's quite complicated, but it actually boils down to a very nice flow chart to help us pick the nonlinearities in our model. So we start here, and the first question we ask is the material behavior linear over the region that we're interested in? And if yes, then we can come over here and use a linear analysis. If the answer is no, then we need to look at operating conditions, and does the material exhibit a rate dependency? And if no, then we can come this way, and if it does, then we go this way. And all of these end up helping us pick the right type of model to use based on material properties. So look through this flow chart and make sure that you can understand it and that it makes sense as to how it progresses through. And certainly make sure that you are aware of these issues that need to be considered when picking a material model. We then come to consider the accuracy of our material data. And if in doubt, vary the material parameters to see how the results are affected. So let the modulus of elasticity go up a little or down a little. Let the yield strength change a little. Let the density change. Be careful when combining data from different sources and make sure they are referring to identical materials and tests. Be careful when extrapolating material data. Finite element software usually doesn't extrapolate material beyond the given values. So if strains exceed the maximum values, usually no further hardening of the material will be considered. If material data are given as an equation, be aware that parameters may not be unique. And frictional behavior and friction coefficients are frequently unknown. So carefully check the parameters you use and check whether the friction law you are using is correct. Not all friction is Coulomb type friction. And here are a couple of websites. Going down our list back here, the next thing we want to talk about are geometry details and simplifications. So coming back down here, we can see that geometry details and simplifications are another important step. And in this category, under this section, the modeler should consider the following things. First, does the entire structure need to be modeled, or can we get away with modeling only part of it? And what details in the full model need to be considered? How was the part made? Was it cast, forged, formed with residual stresses, etc.? Are we sure that the geometry that we're modeling actually is what we're wanting to model? And what are the variations in parts? And what are the tolerances? How accurate does our model need to be? And how well will it compare to what is actually built? And are there possible singularities? So in FEA, stress singularities occur when the stress goes to infinity. So examples of these conditions can be at a point load, or isolated constraints where the reaction would act like a point load. Sharp reentrant corners, inside corners with zero fillet radius. And real structures don't have these situations because there aren't true point loads. There aren't perfect boundaries, and there aren't perfect corners. So often these conditions occur away from the points of interest, and the effects can simply be ignored. However, if they occur near the point of interest, corrective action, such as adding a fillet to a reentrant corner, replacing point loads with equivalent pressure loads, and spreading out displacement boundary constraints over a set of nodes, must be taken. Can symmetry be used? Using a smaller representative portion of a symmetric structure is often done to reduce the size of the model. Symmetry can be used when the geometry, material behavior, and loading are symmetric about the same planes. So just because you have geometry symmetry doesn't necessarily mean that you can have model symmetry, because you might have different material behavior or non-symmetric loading. There are several types of symmetry, including axisymmetry, rotational symmetry, planar or reflective symmetry, and repetitive or translational symmetry. And so check the type of symmetry that you have. Here's an example of an axisymmetric symmetry problem, and here's a linear symmetric problem, where down along this line here we have a repeating geometry. So check the geometry. Importing CAD models for FEA can be very time-consuming and challenging. Great care needs to be taken to ensure that the model complexity is at the right order. The simplest model that accurately represents the desired geometry is the goal. And sometimes importing a CAD model, the CAD model can be extremely complex and detailed, where all of that detail is not needed or even wanted in a finite element model, because it will greatly increase the complexity of the model and possibly prevent a solution from being obtained, or require an extremely large amount of time for a solution to be obtained. So be careful in importing CAD models and just using them by default. Many high-end FEA commercial codes have what they call defeaturing capabilities. And some of these work well and some don't. Even when these commercial codes are used, the modeler needs to go in and verify the geometry. So defeaturing is the process of removing some of the unneeded characteristics in the model, filling in gaps, filling in holes, or removing certain parts and components that don't make a difference in the result, is the idea of defeaturing. Defeaturing can be thought of as simplifying the geometry. The next topic that needs to be considered when planning the analysis is the element type and the options. So we've talked about the element types in great detail, and I will let you read through these comments as I think you will understand them from our previous discussion. Loading needs to be considered, and you need to ask if the loads match the real problem. Again, there are no point loads or moments in real problems. They are distributed loads and distributed moments. There's a St. Venant's principle that refers to having the load sufficiently far away from the points of interest so no localized effects of the force are manifested. It's often good to sum forces on the model and make sure the reaction loads are what you expect them to be. So you can have a truss problem, for example, with loads on it, and you can have the software compute the reaction loads, and the reaction loads better sum to the total applied loads. And that's one good way to check your model, to make sure you have the applied loads that you think you have applied. And buckling should also be considered if it's a possibility, and it should be analyzed. Boundary conditions are where most mistakes are probably made. We need to make sure that the boundary conditions match the actual problem and that it will provide the right solution. So you can have a great mesh, the perfect material model, and one wrong boundary condition will give you completely wrong results. In real problems, there aren't any single point or line constraints. These are theoretical developments that are used in finite element analysis. There are some small area associated with these conditions in real problems, so be careful with fixed supports. There's a Poisson's effect. When you pull on an axial rod in tension, it tends to narrow. A fixed boundary condition won't let that happen, and stress will be developed by the area trying to narrow down. And so you are actually computing a stress due to a phenomena that is completely unwanted. The constraints must prevent rigid body rotation. And this is one of the biggest errors we get. This is one of the most common errors made when learning to do FEA. For example, if you have a simply supported beam as shown below, you will get a pivot error if it's not constrained in the horizontal direction as well as the vertical directions shown. So this small pivot error typically means that you have a boundary condition that is not right, and your model is able to displace off to infinity in some direction. So in this two-dimensional beam, if I come in and I just set this from moving in the vertical direction and the vertical direction, when it deforms, it's likely that I'm going to get a very, very small force in the horizontal direction. And if there's no restraint in that horizontal direction, this beam will move off to infinity. And so I will get a small pivot error, or an error in my software code that says a small pivot error, and I will not be able to obtain a solution unless I also come and fix this beam from moving in the into the page direction. This is also true for the two-member truss shown. A constraint in the z direction can also be required. So here I need to have a constraint in the z direction to prevent this from moving off in the z direction. And this is because small rounding errors in the forces can cause infinite displaces if not constrained. These images here kind of highlight that. If I push down on this truss member here with a vertical load, my member is going to tend to want to go off in this direction. If I don't have it fixed, it's going to move in that direction. And I'll get a small pivot error, which means that the solver can't the solver doesn't have any known values for displacements in that direction, so it can't solve the matrix. Some examples of common boundary condition errors are shown down here. Here, if I have these clamped and I push down on this, you can see the different conditions that develop. So here in the top, I have the same similar truss, and I put a load here on the top, and based on the boundary conditions that I use in this model, you can see how different the results are. If I put a clamped edge on this and push down, these are going to stay fixed. I'll bend in and I will bend in. If I allow this to be on pin joints where there is no moment here at the clamped end and no rotation here, like here I had the rotation, my structure is going to bow out and look like this. If I have this boundary condition where I use a roller, I can see that my member is just going to stretch out. If this end is free to roll and this end is pinned, then my member is going to stretch out like this. And if I pin these two inside corners, I can see that I get rotation to the inside. So here I have a simple truss. So that sums up our discussion on planning the analysis. I would expect you to be able to follow the guidelines discussed in each of these decisions that need to be made to plan a good development of a finite element model. So review those and make sure that you can discuss and talk about each one of these decisions that need to be made. We're now going to continue on with a discussion of the meshing process. And number one, look at the geometry and think about challenge areas such as fillets, rounds, and contacts, high detail, etc., and determine how to handle those areas. We need to determine the appropriate type of meshing based on whether we use what we call a free mesh or a mapped mesh. And free meshing is when the software package uses complex algorithms to mesh the structure. And the user has very little control over the mesh other than the size of the elements. However, the meshing procedure is very fast, and the software typically uses tetrahedral elements by default. The solution time can be very large in these meshes because they are usually very dense. So free meshing is what you've been using so far. You basically push a button and say mesh my structure, and then the finite element software package goes out and based on the quality of the package uses various algorithms to mesh the structure. And because the geometries are sometimes complex, it often defaults to using tetrahedral elements in solid structures as compared to brick elements. So these are nice because all you do is click a button and say mesh my structure. But they can be bad in that they can be very dense meshes and they cannot give you just exactly what you are wanting to need in terms of mesh density or mesh localization, and they can be too dense, requiring a lot of time to solve, where you could get by with a less dense mesh. In what we call mapped meshing, the user has detailed control over the mesh, including the size and type of elements. This is also referred to as unstructured or structured meshing. And I typically do free meshing because it's fast, and then I see if I need to do a map mesh and then do mesh refinement. So if I can take a structure and just click a button and look at the free mesh, and if that's good enough, then I move on. If it's not, then I go back and look at doing a mapped mesh. So we need to consider part symmetry. We need to check the geometry, cleaning up and simplifying or defeaturing any complicated CAD model, in particular small fillets, small holes, duplicate surfaces, and intersections, and those things need to be cleaned up and removed before we mesh. And then element selection. We need to consider the degrees of freedom, the geometry, structure, and the boundary conditions of the problem, and make sure that we're selecting the appropriate element in our mesh. And it is likely that different element types will need to be combined to model the structure. We must take care to make sure that the degrees of freedom of those different element types match, or we write constraint equations between them. And then we use quality checks to verify that our mesh represents the structure that we want it to. Here's a little bit of a discussion on mesh density and solution convergence. So FEA is a process where finite elements are used to model a continuum, and therefore FEA provides approximations to the right answers. The accuracy of the approximation depends on many things, one of which is the density of the finite element mesh. And solution convergence here implies mesh convergence. In mesh convergence, the mesh density is increased until the solution stops changing. So oftentimes when you talk about a converged solution, what you do is you make the mesh finer and finer until the solution doesn't change anymore. The best quote mesh would be the one with the fewest number of elements that provides a solution that does not significantly change when a more dense mesh is used. So mesh convergence sounds simple, but it isn't, and care needs to be taken to make sure the correct boundaries are being modeled and that the element type still makes sense. For example, shell elements could become so small and so dense that they lose their validity and should be replaced with solid elements. And the smallest geometric details that must be captured need to be determined. A sharp corner may cause a stress concentration that needs to be modeled, and the resolution of the mesh would need to be able to capture that effect. However, it may also be that the stress concentration is not important to the problem as a whole. Deformed shape. Consider the deformed shape of the structure and make sure a sufficient number of elements are being used to represent that deformed shape. So we have large deformations. Sometimes our elements can become highly distorted and lose their accuracy. So if we have a high distortion, we need to make sure we have enough elements in there to accurately represent the deformed shape. Deflection or stress. In many cases, fewer elements are required to accurately model the stiffness or deflection than the stress. For example, a one beam element or one shell element can estimate the deflection of a cantilever beam or a rectangular cross section. However, dozens of elements may be needed to compute the stresses. If there's a high stress gradient over a large area, many elements need to be used. And locations to carefully consider are target radii, points of load application, boundary points, attachment points, narrow sections, and abrupt geometry changes. Here are some general meshing guidelines. Quadratic elements have additional nodes at the midpoint of each edge and are normally recommended for structural calculations because linear tetrahedrons are too stiff. So use quadratic elements when possible. For thin-walled geometries, in order to calculate the bending stresses accurately, a minimum of 3 and preferably 5 solid elements through the thickness should be used. So in terms of thin-walled geometries, make sure you have enough elements through the thickness of the thin wall to accurately calculate the stresses. Shell elements are typically recommended for thin-walled structures because so many tetrahedral elements are required to do what shells can do. The removal of small holes, fillets, and chamfers typically leads to a simpler mesh with fewer elements. In the regions where accurate stress calculations are needed, the elements should be of good quality. Many solvers will calculate the results with poor elements, but there will be errors in the calculation. So many advanced software packages will let you do an element check and a quality of element check to see if you have any elements that are potentially giving bad results. A good engineering practice is to break up the structure into simpler elements for inspection and analysis. Pay attention to the transitioning between mesh densities, between a dense mesh and a coarse mesh. Make sure that the transition is gradual. Sharp reentrant or inside corners will result in stress singularities. However, when you add a fillet, the mesh becomes more dense and there are more elements. Exterior corners usually don't need the refinement, and they don't typically cause the same singularities that reentrant or inside corners cause. Try to use elements of consistent size. Don't mix triangular and quad elements. Do not combine element types without understanding all the assumptions and implications to the solution. And model thin plate structures thickness less than 10 times an edge length with shell elements. Continuing with meshing guidelines, if possible, use quad or hex elements. It may be harder to generate the mesh, but the results can be a little more accurate. So use quads instead of tetrahedral. Use quadrilateral elements instead of tetrahedral elements if you can. A fine mesh is needed where gradients in stress and strain are large. Trial run with a coarse mesh may help identify trouble areas. So you can have a coarse mesh, solve the problem, and look for areas where the stresses are high, and then go refine the stresses or the mesh in those locations to improve the mesh and improve the quality of the results and the accuracy of the results. The mesh density depends on the quantities needed. Displacements are often calculated more precisely than strains or stresses because strains involve derivatives. So the differences in displacements between nodes can be less significant. Check shape and size of the elements. Inner angles should not deviate too much from those of a regularly shaped element. As a rule of thumb, adjacent elements should not differ by more than a factor of 2 to 3 in their area or volume. And then finally, sometimes you can start with a distorted mesh that becomes more regularly shaped due to the deformation. So you'd actually use a distorted mesh to fit your geometry, knowing that when you apply the loads, it would become a more uniform mesh. So these are just some of the meshing guidelines that you should be aware of as you develop your skills as a finite element modeler. Make sure that you can know these meshing guidelines and understand them and be able to talk about them. We now want to talk about the second step in finite element modeling, which is solving. So everything we have talked about up till now is dealing with pre-processing and the development of the model. So now we want to just briefly look at some suggestions and ideas behind solving the model. So solvers in commercial FEA software packages are highly developed. There have been thousands of people spend their entire careers developing FEA solvers. And so they are very efficient, very powerful, and highly developed. There are two reasons, though, the solver will not converge to a solution when solving a finite element problem. The first is that the problem definition may be faulty, such as a boundary condition. The second is the chosen solution algorithm and the time steps. So listed below are some suggestions of how to approach convergence issues. If your model is solved without any convergence errors, always still look at the log file written by the solver and check for warning messages. And make sure any warning messages received are understood. To find the cause of the convergence problem, look at the solver log file in the increments before the final error message, and you will likely see warnings that tell you what kind of convergence problem is responsible. If available, look at the unconverged solution and compare it to the last converged time step. So when solving problems, they increment on a time step, and if you can look at the solution previous that did converge, then you can look at why you might look at that model and identify the locations in the model as to where you might be getting a convergence issue. Next, use the post processor to identify the node with the largest residual force and the largest change in displacement in the final increment. And that's what you could do up here if you can obtain a previously converged solution. If the first increment does not converge, set the size of the first increment to a very small value. So if you can change the loading increment or displacement increment to a small value and then solve your model, that can help you identify places where you are having a convergence issue. Sometimes it is the calculation of the material law at an integration point that does not converge. And if this is the case, the material definition may be incorrect or problematic. And you will be able to, you should get an error, a convergence error that will help you identify if that's the problem. Simplify the model step by step to find the reason of the convergence problems. Use simpler material laws, switch off nonlinear geometry, remove external loads, apply more boundary conditions. If the problem persists, create a minimum example and build on it until the problem is found. So here you just go in and you modify the boundary conditions a little bit, you reduce the loads, you use a linear model instead of a nonlinear model. You might remove contact elements or contacts and try to get a model that will solve. And then as you take the model that will solve and work it towards the model that you need, you can identify where the convergence issues come in. This is probably the most commonly followed approach to finding convergence issues. Finite element programs use default values to control the Newton iterations. If convergence is not reached after a fixed number of iterations, the time step is cut back. In strongly nonlinear problems, these default values may be too tight, and you may need to increase the number of iterations. Depending on the software, there may be more options to tune the solution process. Some software allows for an initial guess for the solution of a time increment that is calculated by extrapolation from the previous steps. This usually improves convergence. Be careful changing the solution controls, and only do so if you know exactly what you are doing. An example of where the controls may need to be changed is when the stress is concentrated in a very small area of a large structure. So there are lots of settings that you can go in and change in the software, but make sure you understand what those setting changes are actually doing to the solution process, because you can change the solution so you're not actually getting what you think you are getting. Contact problems sometimes do not converge due to problems in establishing which nodes are in contact. And so be careful with contact elements and remove them if you are getting convergence issues, and then work them back in and try them gradually as you get the problem to solve. This is about all we're going to say about the solving of the solution and the solving process. Again, remember that these solvers are extremely complex and very powerful, but they do have their issues, and we need to make sure that we know how to modify the solver and use the right solver for the problems that we are trying to solve. The next step and the final step that we're briefly going to discuss is post-processing. So we talked about the first step of pre-processing, then the solving step, and the final step is post-processing. And there are two aspects to checking a model, that is, checking to see if our model is correct. First is the model verification, where it is shown that the model was correctly specified and actually does what it was created to do. This includes looking at the loads and the boundary conditions and the material behavior and so forth. And the second is the validation, which means to check the model by making an independent prediction, such as hand calculations, experimental testing, and so forth. So in verifying the model, we need to check the plausibility of the results. If the simulation deviates from intuition, continue checking. Never believe a simulation result that you don't understand. Either the model or your understanding is wrong. So work on that until your understanding and the model you have match. In either case, it's important to understand the effects. So check your explanations for the solution. For example, if you assume that thermal expansion is the main cause of the stress, run the model by letting the thermal coefficient of expansion be 0 and show that the stress is small compared to the stress when the proper thermal coefficient of expansion is used. In 3D simulations, cut the structure and look at the inside stresses. Don't just accept the surface stresses. Cut the model and look inside to validate the results. You will want to make sure you do this in all of your finite element models, and particularly your final project where you're looking at the stresses in a bracket. You want to cut that bracket and make sure that the stresses make sense inside the bracket. Calculate check the boundary conditions and make sure the nodes are constrained as expected. If you set a boundary condition to be 0 at a certain location, make sure that it is 0 at that location. Check the mesh density, showing that the results have converged. Go back and refine your mesh and recompute the values and see if they've changed. Check that the stresses are continuous between elements. At interfaces between different materials, check that normal stresses and tangential strains are continuous. Check that the normal stress at any free surface is 0. If linear was assumed, check that the strains and deformations are small enough to justify the linear assumption. And be careful with rainbow color spectrum plots. Gradients may be difficult to interpret because of human perception of the colors. And an example of this is shown on this page here. The above plot shows a bar under bending and tension. In the rainbow plot, it is difficult to see whether the gradient is homogeneous or not and to find the line of 0 stress. A divergent spectrum with a neutral color at a 0 makes understanding the stress field much easier. So in this case, we can see this stress field more clearly than in this case here, and where the stresses are 0 and different types of plots of the results can highlight answers that make them more clearly understood. Validating the model. If possible, use your model to make an independent prediction that can be tested. And a good reference is down here by Martin Baker in how to get meaningful and correct results from your finite element model. So this concludes our discussion of the theory behind finite element modeling. Hopefully it's been beneficial to you, and you now have a much better understanding of the 3 steps of pre-processing, solving, and post